lot of challenges, well, similar challenges on these glass handrail jobs. But basically the architects and the manufacturers aren't doing us a ton of favors because we're speccing out 1/2-inch handrail, and as our analysis gets more advanced, we're starting to find all these stress risers, and we're finding out that 1/2-inch handrail doesn't work for a lot of situations, and it's causing a transition that's always kind of a pain point. So we wanted to kind of get out ahead of it, especially for you guys, and kind of show you all of our engineering, kind of show you what we go through so that you guys can have, like I said, kind of a cheat sheet. I think I said last time, a lot of this stuff is in, you know, in emails and phone calls on job to job, but we just thought it'd be good that you guys have it right there for you when you're bidding jobs, just so you have it in the back of your head. So we're not surprising you. But I also added a little bit more meat to the beginning to just talk about glass in general, just a little bit, and why glass is so tricky. And basically it's because glass is very brittle. So the opposite of that would be ductile. So to talk about that, basically steel, extremely ductile. So steel, when you start pulling it, it's going to go a long ways before it actually snaps. So if anything is happening to a steel structure like a floor system or something, it's going to deflect a long ways before anything catastrophic happens, so people can get the heck out of there, basically. Glass isn't like that, it's just going to go. Same with like concrete. So concrete is also really brittle, that's why we have to add rebar. So when the concrete's in tension, you have a rebar and lots of safety in the fact that if it starts over deflecting, people can get out of it. That's why we have to be safer with glass. We can't reinforce it with rebar, you know, it's just glass. And it's supporting humans, and so it's not giving us a lot of signs before it goes, so therefore it's a greater risk to public safety. So that's kind of why we have to be careful with it.
Hey, what percentage is your business switched from monolithic to laminate on handrail?
It's slowly getting there, and that's kind of where this presentation is coming from. It's more monolithic, but it's, as the 2015 code has come out, it's starting to force a transition to laminate, and so I've seen more, but I don't know that we have a good percentage-wise. I kind of see...
Right now, it's probably about half and half that we see.
Is it fair to say that everything's changing, they want laminate, so it doesn't vacate the opening?
Yeah.
And then do your calculations have to go to the thinnest light of a laminate, or like we use a lot of 1/2-inch tempered glass. I think you even say your standard is 1/2-inch. When you go laminate, does one of the lights have to be 1/2-inch to make the load, or can 2/4 be?
So that's another...
Is a laminate considered structurally like a monolithic? Just curious.
It kind of depends on how you look at it. So that's kind of another discussion. That's like a post-breakage type analysis,
Yeah.
I think you're talking about. So that's looking at a laminated handrail without a top cap, is kind of what you're discussing. If that's the situation, then there is an acceptance criteria, AC 439, that does say you need to consider one light broken and the other light has to kind of remain in place to help the loads if there's no other top cap or some other bracing mechanism.
The international code.
Yeah, ICC. So yes, yeah. But
I'm not so sure. With or without a top cap, if it's 1/2-inch tempered and it's a 3-story mall and it breaks from somebody broke it or nickel sulfide inclusion, and a kid rolls off the 3rd floor, it's a problem. So, like, I haven't walked through a mall renovated in the last 3 years, and my wife takes me to a lot of malls that's not already laminated. So I would have thought the percentage would already been north of 50%, but because a lot of the lineal footage I see going in new construction or renovation is laminated.
And that's
I just
kind
wanted
of
to confirm it, but.
Yeah, that's kind of the trick of it, and why we're kind of talking about it today, is because Europe is ahead of us in some ways. So our finite element package is out of Europe. It's a German-based program. So we're finding all these stress risers in our glass.
Yep.
But a lot of their glass, in talking with the guy who runs that program, they've already done that in Europe. So all glass is already standard 3/8 on 3H. We just haven't gotten there yet in the US. So architects are still speccing things that aren't overcoming those issues. So that's kind of what we're in.
And a lot of it is regional too, because there's a lot of places that have not adopted the new standards for the IBC yet within their own code criteria. So like New York, we get up into New York, we do a lot of stuff up there. They're still going back to like you know, IBC, that, you know, their model is based off of the
2006.
old
Yeah.
IBC 6.
Yeah.
Yeah. So it's something that as engineers, I like that. As engineers, we'd love it if it was half on half, because then it covers everything.
Yeah.
And it's really safe, but.
We would too, as far as markup on cost, so.
Yeah.
The bottom line is every handrail we look at from estimating, or if we've already got to project management, we're calling you guys, and these guys are doing engineering and shop drawings of our handrails.
Yeah.
So we're kind of
challenge-
covered by code with you guys doing all of our work, including new anchors.
Yeah.
Is that fair to say?
Yeah.
We don't use anyone else?
Right, they cover us.
And there's no need to.
That's part of why, you know, as part of our value add.
With the changes, they probably need someone like you, because their people don't know the handrail code changes either. So
Yeah.
you gotta keep up with the training.
Yeah.
I think this industry's changed a little bit.
It is.
Absolutely.
Yeah.
Okay, well, yeah, the thing with these is their averages. So what I wanted to touch on here is, mostly with laminated glass handrails, we're at fully tempered, so we're at 24,000 PSI. That's an average breakage. So they could have a good day at the float glass factory and it gets up a little bit higher than that. They could have a bad day and it gets down a little bit lower, but that's ultimately an average. So it's kind of honing in on, again, that this is a pretty brittle material, so we're still dealing with like safety factor analysis. So we wouldn't obviously design, again, for a kid pushing up against that all the way up to that design strength, we'll bring it down to kind of help for the fact that it's variable.
And we won't do that just off of our own internal factors of safety. It's based off of code required factors of safety. Yeah.
And then just break patterns, I kind of put that in there. The reason why we like tempered is because it goes into tiny little fragments and yields big shards. So that's not super relevant to handrails because we've already kind of gotten past that. This just kind of shows you some of the probability of breakage type things. So it's kind of a level of safety already and where I'm kind of leading into the code safety factors. So railings is we want to design so that it's much less than 1 to 1,000. And I kept this other stuff in there for kind of reference. So like normally our curtain wall systems, storefront systems that we design, we assume that it's going to be 8 crates in 1,000. And so obviously we don't want that to happen on railings because it's keeping people from falling down to lower levels. So we bring that down to much less than 1 to 1,000. And that's represented in a safety factor that we'll get into when we get to the code. Guardrail design, when you're dealing with monolithic rails, time and temperature doesn't matter so much. It's when you start getting into the laminated stuff. Laminate actually, and I'll go into it even further, laminate is time and temperature dependent. So it's not like a linear deal. So if you have a snow load sitting on a glass canopy, the longer it sits on there, the more of a risk it is of it breaking. And the laminate actually gets mushier. And the longer it's out in a temperature, the longer it heats up, it gets mushier, so it allows some slippage in glass pipe. We'll go into that a little bit more. This is just kind of an introduction to it a little bit. But this kind of gets into the meat that we kind of talked about last time of what we have to consider for glass handrails. So these are our load considerations. We've got a 50 pounds per foot pedestrian load. So that's just people kind of leaning on the glass if you're brave enough. 200 pound concentrated load. That's someone tripping and falling into the glass, something like that. It's an actual fall hazard, so keeping them from falling to the lower level. And then wind. Wind, typically, the good thing about wind is, so the top two have a higher factor of safety, which I'll go into, because we have human loads present. Wind allows us to go back up higher, so we don't have as stringent of a safety factor, because the idea is, picture a parapet that's also a handrail up on the top of the building. You assume when you've got a high wind situation, if you've got a storm event, you hope no one's standing out on a exposed balcony grabbing onto the handrail kind of thing. So it's just a wind load, and the code says we don't have to consider those together. So we get a little bit higher, so it's in there, but it doesn't cause more of an issue, even though parapets do have a lot higher loads. It could in certain situations, so it's good to watch out for them. Because it's not like a normal load, you've got load on both sides of your glass. But, and more often than not, the top two loads are what's most important.
Hey, you've got the J-edge anchor on that, back up. You're using a drawing where this anchor is connecting.
Yeah.
Yeah, so this is like a situation where you've got a bolted angle and you could use the JEI anchor and bolt right down to there with the CRL handrail. You could also, I think it's in here later, Stuart kind of added a fascia mounted, because the CRL has the fascia mounted options too. You could do that as well with this.
Just run into the edge.
Yeah, you could just run the bolt right into that, yeah.
Really, you can bolt anything to it, right? I mean, it's designed so you can bolt a variety of external
Almost
things.
any facade, yeah.
Hey, sorry, another dumb question, because I'm the new guy. Do you just do design and then we procure all this stuff, or do you guys have the one-piece shoe and
No,
get the glass, or?
yeah, we're not a supplier.
Okay,
Just
so you're just
engineers.
getting us the shop
engineering.
drawings, and then we're buying things from, wherever we buy our one-piece shoe and glass from, whoever it is, Tempered Glass.
Yeah.
Typically, we provide them the shop drawings for the engineer.
Brett Temple is usually providing the shop.
Okay, that's a connection with Brett. He does the shops, you guys calc it.
Yeah.
You calculate, make sure the shots line up.
You have a little discussion before he finishes all the shots on what the concept of the design is, and he does, then you calc.
Yeah.
Okay.
Yeah, we basically, our process is we put together our calc package and put red line comments on the
Mhm.
approved shop drawing. Then we send those to you guys to approve, Brett, or whoever updates them, and then we have our field set that line up.
He wouldn't come, but he had a kid thing, so he lives in Wichita.
Oh, yeah, so one drive.
And do you do engineering calcs for our other walls as well? Okay. All right.
All we do though is glass and glazing and panel stuff. We don't do general building engineering. We're focused
So
in
we
glass
won't
and glazing
have,
industry.
we won't show up in a job where you're also the engineer for the project.
Right.
No, yeah.
No.
No.
All right, so you're an engineering firm that today you're giving us a handrail.
Yeah, we're just
Okay.
focused on glass and glazing industry only, that niche.
Great.
Yeah, we have some,
So we know everything
basically,
about it. We're sharp in it.
Matt came and did, they came and did a presentation a couple months ago on their JEI anchor, and they kind of had this handout ready, and they went over it a little bit. But like Ian's had some handrail job, I have some handrail job now that's kind of incorporating some of these
Mhm.
changes, so we thought we'd have them come back and just do a full-on handrail.
Yeah, good idea. But for a company, your business, you're mainly like without the owner consulting piece, you're like a small CDC in the sense, or,
Yeah,
We'd like to
right,
be like
one
more like
design
a-
group.
yeah,
Yeah.
okay.
So now into the challenges, I guess. We start with the 2012 code. To what we have to consider from the 2012 code, we can still use monolithic glass as long as you've got a top cap. There's our safety factor. The code requires safety factor of 4. So, and then yeah, we're requiring a top cap for a monolithic glass. And the top cap, this is where we get into the AC 439 discussion. It basically lines out that that top cap has to be present and able to take a load should lights fail. Because like we said, you've got nickel sulfide inclusions, you've got anything that can happen to these glass pieces. So if that light breaks and it's monolithic, it's gone. So we want to make sure we have a top cap that can support a load and help someone. The idea is to help someone from falling and get them back to safety. Like
So
for instance,
what's the logic on that? Let's say it's a 100-foot run and the top cap is 12 foot long and the modules are 5 foot. Your assumption is 2 lights aren't gonna break next to each other at the same time?
yeah.
Because it's not like they go over and anchor the side of the building, right?
Yeah,
And that's,
If it's more than, if your top cap is more than the width of a piece of glass and that glass breaks, it's gonna be anchored to the light next to it at the top, so the top cap would still be there.
right, yeah.
If both lights broke, the top cap would go with them, right? What? Are you getting?
It always has to be supported by 3. That's another code requirement. So that has
Okay,
to-
that's what I was getting at, is
Yeah.
there, so now 3 would have to break.
Yeah, so it
Okay.
always has to be a minimum of 3 balusters supporting your top cap. So the idea from AC 439 is, it still is, we don't consider 2 lights breaking. So it'd be either a center light where you still have a top cap that spans between 2, or an end light where you have the top cap cantilevering off the end. Now the code,
I like the 3, because 2 really could break at the same time if they both, the reason they broke is an edge disruption, the edges are right next to each other, so.
yeah.
The kid put a hammer in there, it could break 2 at a time, right?
Mhm.
In
And
a case like that where you have two lights, the top cap then needs to be anchored to structure so that if you do have two lights break, you still
Yeah.
have that top cap.
Yeah, when you don't meet the 3, then you have another way to do it, but it's probably anchoring the top cap to something like a
Yes.
jam.
Yeah.
I'm with you.
And really what this is for is for a fall. So it's for like someone running into it. And even though we've designed for that, the unforeseen happening, maybe he has, I don't know, something sharp on his hip or whatever in it, or it is has nickel sulfide inclusions or something and it breaks, we want to make sure that that person is braced and can get up, get back, and then they can caution tape it and replace the light. It's kind of the idea. That's essentially what we're designing for. And so, like for instance, what I was going to mention is it lets out some of the requirements. So like the maximum deflection allowed at that point on this tab cap is like 12 inches. So it's not like we're designing it like a curtain wall or storefront system. It's just a last case scenario. So that's 2012 code and this is where we start transitioning into where they're kind of forcing the laminated issue as another layer of safety, essentially.
Times square.
I was gonna say, it's Times Square.
Yeah.
So basically, when they went over to the 2015 code, they said anywhere. So the 2012 code protected people up above. 2015 starts also protecting people down below. And so essentially, by forcing the laminated requirement, except on areas where you have walking surfaces below, what that means is even if you are using PVB or a lesser inner layer, if that thing breaks, it's going to flop and remain in the chute. So it's not going to fall on the people down below. That's kind of what the laminated glass requirement causes. The problem is, I don't know that they completely knew that it's a completely different design. Laminated glass, and I'll get into this, half-inch laminated glass is not equivalent to half-inch monolithic. It's a trickier issue. But we still have the safety factor 4. It still requires a top cap unless it's approved by a building official. And that kind of gets into, you still want that safety factor. You still have all the exact same stuff. They just added that caveat for the laminated glass. So we still want to protect people up above, to protect the people down below, and then if the glass breaks, we still want a second layer of safety to make sure that everybody's okay. And then also testing and stuff. So that's kind of where we transitioned and where we started adding a second challenge, because up until now, we were kind of dealing a lot with challenge number 1 with monolithic glass. This is due to, like I was mentioning before, finite element modeling. We started noticing stress risers and that our standard calculation methods weren't really covering what could actually happen out in the field. And this is, covers with is in line with C.R. Lawrence and those guys with covering basically what I'm trying to get at is challenge number 1, we have to consider that 200-pound concentrated load at any point along this glass. What we found out is if you've got that end light situation and that top cap isn't attached to anything and someone runs into the end, that causes a huge problem because you're distributing this 200-pound load into a smaller section of glass, causing higher stresses. So that's our first challenge that we still have, even going from 2012 to 2015. But this was like the bulk of the challenge. So it wasn't as hard of a conversation all the time. It was like, hey, we got to worry about this end light. And we figure it out with these solutions. You do have to look at pre-break and post-break. So pre-break is the glass there. So it's not broken, obviously the glass is supporting the load. If you have this issue, 200-pound load at an edge where there's nothing attaching to it, your solutions are thicken the glass, attach the top cap to structure like Matt was alluding to, or use a heavier top cap. I've gotten some to work where you, instead of using like the beauty cap, you use a nice thick heavy structural cap and you even run it down the edge because it allows that, if you run it down the edge, it allows this load to spread out a little bit, kind of stiffens that edge. So it doesn't take such a direct pat down to the chute. So those are some quick solutions to that. Post-break is where the glass is gone, like we were talking about. This is the acceptance criteria, it's the backup plan. The glass is gone and we need the top cap, right, to make sure nobody falls down. So when you have those 3 lights that we talked about and the end light breaks, this is the situation you have. Your glass is gone and you have a cantilever and you have to support someone with that cantilever. The only way to fix that is you have to shorten your glass length. So I don't know if any of you guys have seen some of the updated ESR reports for CR Lawrence, where they have a top cap and they list out the maximum spans. That's what they're doing. They're telling you, hey, you got to shorten this end glass length so that when that end light breaks, it's not spanning so far to the next piece of glass. Same with in between the two pieces. So you still have your three. If your middle one breaks, those are a lot easier because it's fixed on both ends, so it's not diving inward. Yeah. Then you still have the same solution. Attach the top cap to structure. We can throw that 200 pounds right into the structure, and then use a heavier top cap. So that heavier top cap would let you lengthen your glass out so it can take a longer cantilever. So this was kind of always there. The more challenging one is when we start getting into laminated glass. So this was what I was kind of alluding to, where half-inch monolithic isn't exactly the same as half-inch laminated. And these are some of the reasons. So you still have challenge one, obviously, even with laminated glass. But with laminated, you start to get into beam theory. So the best analogy I have for this, if you can picture stacking like a couple of 2x4s on top of each other, walking across that and getting to the center and it's spanning between two things, and you can like kind of bounce on it, it's bouncier because it's spreading, it's not as stiff. You're basically asking the 2x4s, each of those 2x4s to take each of the load because of the slippage at the ends. So in this example, you've got P on there, and each of those is taking half of P. So that's kind of, if you just think of it that way, you get out, you've got 2x4s setting on their side, so stacked on top of each other, and you kind of get out, it's a little bouncier. Now if you take that same 2x4 and turn it vertically and you go out to the center, it's not going to be as bouncy. Does that make sense? I know I kind of like, that was the best way I can think of to describe beam theory.
Or a solid 4x4.
A solid
Yeah,
4x4.
Yeah.
You get a much stronger moment of inertia structurally by deepening the member. So that was kind of what's going on. So basically that's why when you have two pieces of 1/4 inch glass, it's not really acting as one piece of 1/2 inch until you have a strong enough glue. And that's what I kind of alluded to there. It's only as strong as the stiffness of the inner layer that you got in there. And so there's also temperature effects. And because inner layer is nonlinear, it's affected by the temperature. So the longer you keep it out in the sun, the more it softens and the more those layers slip in between each other. So that's kind of like what the trick of laminated design is, laminated glass design is. These are the solutions. So the solutions get a little bit more in depth because you have to break them out a little bit. The number one solution is it has to be SGP. And 9 times out of 10 cases, anytime you have the human impact, the 200-pound load, you can't get PVB to work because of how much slippage there is in between the lines. It's basically like mush, peanut butter, Stuart kind of puts it. Especially if it's outside, it's just nothing. The values, I should have printed that, I guess. Like if you're comparing the stiffness values, it's orders of magnitude bigger when you go to SGB. Solutions for these guys?
We were actually at a glass build show a few years back, and we were talking to CR Lawrence. And at that point, they said, we're going to SGP on everything that they do in terms of glass handrail systems, just because of that.
Yeah, and what I was alluding to earlier with going to 2015 code, where I got that from is they showed us some testing, and SGP, if everything breaks, all your glass breaks, SGP is strong enough it still actually stays vertical, where PVB just flops over, like I said. So it's just even for that reason, it's safer. But it gives you a ton of strength. So we can actually start spreading out that load better. It's all the same kind of idea. So interior, 2012, 2015, all the codes. This is where we kind of added value. We've found ways to make those work. With our finite element package, we've done some extra analysis in the background, and we've found workarounds and solutions to this to keep using the 1/2 inch glass for now. And so we can get them to work, they're safe. We still have to solve challenge number one. There's no way around that one. That is, the glass just can't take it, the 200 pound in the corner. So we have to kind of still spread that load out. Exterior is where it gets hard because of the temperature effects. So 2012, The easiest solution, if it's possible, is go back to monolithic. You're still within code. Make sure you have that safety factor built in with the AC 439 and all that we've talked about, where the lights break, and solve your challenge number one, or you have to increase the glass thickness. So we've found a workaround for the 2012 code is to go back to monolithic because it's stronger. You're getting rid of that weak glue effect when it gets heated up on the outside. Because even SGP, when it gets heated up, it's still weaker. It's still a non-linear type material. Exterior is the official, if we have an exterior, a 2015 code, there's just no way around getting, and it's a true guard hazard, there's no way around getting that to work without increasing the glass thickness. It just gets heated up out there, even with PVB, if you're using laminated glass. And this again assumes that we're using 1/2 inch, which is kind of the industry standard in the US currently. 1/2 inch laminated, it's impossible, long story short. So that's the one pain point that we have to increase glass. So that's what I wanted to, basically we've done a lot of the workaround, and the reason for this presentation is we were finding all these deals, and I wanted to go through and show like, hey, this is the one to really look for. If you see a 2015 IBC and they're showing 1/2 inch laminated glass, there's no magic that we can perform. So that was kind of the reason behind this presentation, or one of the reasons. We also wanted to share, so the New York job that we showed in that picture before, we did a little bit of work on this. Stuart wanted me to kind of share this a little bit.
We were involved as an expert witness.
Right.
On that project.
Expert witness on that guy. And this is, everything I've talked about before is mostly speaking in terms of stress, making sure the glass doesn't break. There also are code requirements for deflection. They're not as hard of limits because they're kind of just, we found them in specs. I don't know that I've ever seen one in an actual code.
Yeah.
So we try to, for safety, so basically 1 inch or H over 50 is a way to make sure that that railing doesn't feel spongy and make you feel uneasy when you're walking through a building and leaning up against it, is what I've deciphered. But when we run our analysis, a lot of times engineers, we run it based on the glass and check for 1 inch deflection to see if it's wobbly. What we ran into on a job was it wasn't actually shimmed correctly, and there was some wobble built into the actual structure. So that's something to watch out for whenever you have these base shoes. And you know, the reason why it got brought up is it was a balcony for, it was a hotel, is that right?
Yeah.
And
or a
I mean, people are-
condominium.
and they're out there, they're right there all the time pushing up against it, and it was like, it was really uneasy.
It was right in Times Square. They were doing a renovation. They were putting in these high dollar, fancy glass rails. And the general contractor, after these glass rails got up, the general contractor happened to be walking by one day, caught a hold of a corner of it, and it moved excessively. And therefore, he said, this is not safe. We're going to investigate. They hired a third party. Third party came in and basically said, oh no, it's under design. And then that's whenever we got involved as being an expert witness for another client that actually designed it. And so we basically came back to the fact that a lot of it's being caused by the stiffness of the shims and all the other stuff. But there were a couple little areas at the corner locations where we had, like that challenge number 1, we could not defend. And so they basically making that client change out a lot of nice high dollar.
Fired as one.
Yeah.
Yeah.
So the importance of that is you got to make sure it is set up stiff to begin with, on a stiff attachment point, because otherwise there's going to be some automatic wobble in it that maybe somebody throw up their hands, architect walking through and saying, oh, this is not right, and then all of a sudden then you got a big deal on your hands.
We had another local guardrail project recently. We had somebody call us and said they were out there, they just started pushing on it, and the thing was wobbling.
Yeah.
We went back, checked through all the numbers, and ultimately found it was an installation issue. But yeah, that's the stuff we need to be aware of on projects like this.
Because ultimately we definitely wanted to, why I wanted to bring it up today too is usually we're so focused on stress, making sure the glass doesn't break, and then we're like, okay, we're a little over our deflection. Is the architect okay with this? It's just going to feel spongy. But in some cases, deflection can be a big issue as well. they can kind of drive the bus. So it's something to kind of keep an eye on. So this is the cheat sheet, essentially on the back page that I kind of put together. And basically it was and I can, reword it however you guys want or whatever makes it more beneficial for you guys. But I wanted to give you something, long story short, basically to really watch out for those exterior rails with the 2015 IBC. Not that that's the end all, but that's one that like we can't help much on. It's so hard to figure out. There's a lot of other like workarounds that we've always worked on for the other stuff, but this one, it just doesn't work. So the 2012, so this, like I said, cheat sheet, 2012 IBC or earlier, try to use monolithic rails as much as humanly possible. If we can't, we still have that laminated issue. But 2012 IBC allows the monolithic with the rail cap, and then you just have to solve challenge number 1. And then again, 2015 IBC or later, we can still get interior rails to work with our finite element package. And then we have challenge number 1, but we need SGP to give us a fighting chance on the interior ones. And then 2015 exterior, that's the guy. So we got to use SGP, and we have to increase grass thickness to like a 3/8 on 3/8 at least. That kind of gives us something to work with.
Hey Matt, can you back up to the 2015 IBC where they're talking about the exception for not having a top cap? I think Chuck had a question about that, originally. Do we have to design each individual ply if we're using laminated glass under that exception? Can you talk a little bit about that?
Yeah, so basically what we've talked about is I've assumed kind of requiring the top cap. If an architect or the look wants to go with completely without a top cap and 2 pieces of laminated glass, we still have to we still have to adhere to the AC 439. And that's where you say, okay, we need that backup plan in place, and the only thing we have there is the glass. So in that case, we have to design for if one light is broken, same situation, you've got the 3 lights or whatever, that light is broken, we want the other light to be able to support the load to make sure that person doesn't fall over. So it's a redundant.
Yeah, you gave the answer kind of in your example of standing on the 2x4 upside, but I mean the answer is you have to do your calculations to the thinnest light of glass.
Yeah.
So if it's 1/2 inch tempered to 1/2 inch lamy, you have to do all your calculations based on one of those pieces of the lamy and the thinnest one.
Yeah.
I think it's the engineering answer.
Yeah.
But,
Yep, exactly.
and I kind of knew that a little bit. I was just questioning you a little bit, and I wanted to see kind of where the current codes were, but I think you did a great job getting this group about what's going on, right?
I think the one exception for that doesn't, when we design to the 1 ply, we're not using that safety factor for.
Yeah, we have some helps. It's
Right.
like an
Because something's already been broke, so it's actually we can go up higher in stress.
So they let
to
you
prevent
allow,
somebody
they let your thinking on safety factor be a little differently because of the practicality of what's happening.
Yeah.
Because you'd never be able to get, with a safety factor of 4, you're not going to get a 1/4 inch ply to work
Yeah.
at all.
Yeah,
It's the same idea as the
yeah,
top
that makes
cap.
sense.
They let the top cap out to a 12-inch deflection. It's that same idea. We don't have to design for service conditions again. It's just to get everybody away from it. And
Yeah.
then rope it off.
Yeah, I was surprised to hear that 12-inch too. That kind of caught me off guard, but that's what it is, huh?
Yeah, it's 12 inches. Like I said, it's just the light is broken and it's moved, so it's to make sure they don't fall. It doesn't yield, it doesn't break, and then you get them away.
The other caveat to that is also there's only that exception if the building official approves it. And so ultimately what that means is that you have to have a building official involved in the design process. Because otherwise, it could go down the line and not be approved.
Yeah.
It holds everything up.
Didn't we, we had
Yeah,
the city
KCU.
approve that we didn't have to have that top cap
Yeah.
on the one project.
Yeah.
Are we seeing more designs without the top cap? Because sometimes I remember hearing you guys talking about they're not using the top cap as much, or they are using it.
I feel like it's more and more they're using it.
They're using it.
Because it's a lot harder to get just a laminated to work. You have to increase the thickness, and like the reason why, like the industry standard is 1/2 inch, so if you start bucking the industry standard by using those laminated, it just causes a lot of pain points. So the top cap usually gets put on.
Yeah.
That's what I've seen.
Usually the low profile top caps, the most minimal profile.
Low profile top caps, yeah, maybe
Doesn't
that's
help
it.
much with.
Any other questions? current job.
Great job, man.